Hello, everyone. My name is Zhengyan Lun from UC Berkeley and Lawrence Berkeley National Lab. I'm supervised by Professor Gerben Seder. Today, I'm going to talk about our recent publication on Nature Materials about cation disorder rocksalt type high entropy cathodes for lithium-ion batteries. During the past 15 to 20 years, the research on lithium-ion cathodes is dominated by the so-called layered rocksalt structure, as shown in this figure. The layered rocksalt structure has separated lithium layers and transition metal layers. And the lithium migration happens along these 2D lithium layers. And within this layered rocksalt structure, there are several types of popular chemistries, including lithium cobalt oxide, the LCO type structure, and the lithium cobalt nickel manganese oxide, the so-called NCEM structure, and also the lithium cobalt nickel aluminum oxide, the so-called NCA structure. The reason why most of the layered rocksalt chemistry heavily relies on cobalt, nickel, or manganese is because they do not tend to migrate from the transition metal layer to the lithium layers, even after lithium delithiation. And that will prevent the structure from irreversible structural degradation. And in contrary, when we talk about cation disorder rocksalt cathodes or DRS cathode, it represents the structure that does not have separated lithium layers and transition metal layers, as shown in this figure. Or in other words, all the lithium and transition metal ions are distributed randomly on all the cation sites. And because of this, now we can see in the DRX chemical space, compared to that of the layered rocksalt structure, we are not only able to use manganese, cobalt, nickel. Now we are open to more transition metals such as titanium, niobium, vanadium, chromium, molybdenum, etc. And this is extremely helpful to resolve the source issue of cobalt as well as nickel. And that paves the way for the development of electric vehicles as well as large-scale energy storage. Actually, for quite a long time, people believe that fast lithium-ion diffusion in DRX material is not possible because of cation disordering. However, later researchers found that this is not correct. Although in both layered rocksalt and disorder rocksalt, lithium migration happens through this OTO mechanism, which means the lithium migrate from one octahedral site to the neighboring octahedral site through this intermediate tetrahedral sites. It happens via different tetrahedral coordination environment. In layered rocksalt, the lithium migration mainly happens through this 1TM migration channel, in which the intermediate tetrahedral sites is coordinated by one transition metal and 3 lithium. That's why it's called 1TM channel. However, in DRX material, this type of 1TM channel is no longer active for lithium transport. Instead, the lithium transport heavily rely on this so-called 0TM channel, in which the intermediate tetrahedral sites along the lithium migration pathway is coordinated by 0 transition metal. That's why it's called 0TM channel. NEB calculation on lithium migration barrier can help us understand why there is such difference. In this figure, it shows the OTO lithium migration barrier versus the average tetrahedral height, which represent the size of the intermediate tetrahedral site along the lithium migration path. As we can see, when there is a large tetrahedral height, which is the case for layered rocksalt structure, the lithium migration barrier along 0TM pathway versus the lithium migration barrier along the 1TM pathway is not that different. However, in DRX material, the average tetrahedral height will be reduced because of cation mixing, which can be represented within the shaded region in the figure. Now we can see the migration barrier along the 0TM channel is significantly lower compared to that along the 1TM channel. And that's why in a disordered rock salt structure, this type of 1TM channel migration is no longer active because of the much raised migration barrier. As we can also see from the calculation results, the lithium migration barrier along 0TM channel in DRX material is comparable to that along 1TM channel in layered rock salt structure, which means in DRX material, lithium migration can be activated mainly through this 0TM channel. In other words, the lithium transport in DRX material is largely determined by how frequently this type of 0TM tetrahedron appears and how these 0TM tetrahedral units connected with each other. Although there is no long-range ordering on the cation sublattices, there can be significant amount of short-range ordering appear on the cation sublattices, which would influence the frequency as well as connectivity of 0TM units. And this will further controls the capacity and rate capability of DRX materials. Here is a comparison between a DRX material, lithium manganese titanium oxide, and another DRX material, lithium manganese zirconium oxide. They are very similar in chemistry. However, as we can see later, they will have very different electrochemical performance. DEM electron diffraction can be a useful tool to characterize the short-range order in DRX materials. As we can see from the two electron diffraction images shown here, the round spots represent the long-range order feature, and we can see both materials demonstrate the same long-range ordering. And these diffuse patterns here demonstrate the short-range order, and we can see the two materials shows quite different diffuse patterns, which means they have very different short-range order type. As a consequence, we can see the LMTO material obviously have a higher capacity, which means more lithium is electrochemically active in LMTO because of this type of short-range order compared to LMZO, where less lithium is electrochemically active, and that is controlled by this type of short-range order. And the difference in short-range order and electrochemical performance is further corroborated by Monte Carlo simulations. Here in the simulation results, the lithium are connected to the 0TM migration path are connected with these green bonds in the figure. As we can see, LMZO has significantly less 0TM connected lithium because of this unfavorable short-range order, while LMTO have more 0TM connected lithium because of the other type of short-range order. And extensive Monte Carlo simulation on various different chemical space shown here in this figure actually demonstrate that most of the short-range order is actually harmful, because here is the theoretical value of percolating lithium if we assume the structure is completely random or there is no such short-range order. It can achieve almost 80% of lithium that is connected to the 0TM network. However, in real system, because of the presence of short-range order, the exact amount of percolating lithium is significantly reduced compared to that in the random limit. In other words, the short-range order will negatively influence the lithium transport property in DRX material. So we have a wish here. That is, if we can somehow break the short-range order in DRX material, we are expected to improve the lithium transport property. Okay, how can we achieve that? We start from basic thermodynamics. Delta G equals delta H minus T delta S. We want to minimize delta G so that there can be less short-range order. Obviously, there are two strategies. First is to increase the synthesis temperature so that this term becomes more negative and the delta G can be reduced. However, as demonstrated by previous study, the synthesis temperature for typical DRX is already very high. It usually reaches around 900 degrees C or 1000 degrees C. So there is really not much space for us to further increase the synthesis temperature. And then the second strategy is if we can somehow increase the entropy term so that this product also becomes more negative, we can also decrease the overall Gibbs free energy change for this reaction. And we can also expect to reduce the short-range order. So that comes to the second strategy, that is to increase the number of transition metals in DRX so that we can benefit from the entropy effect. Actually, this strategy is promising because in some recent publication on high entropy oxide compounds, the excess results suggest very similar local configuration for each transition metal, which means there is really very small amount of short-range order that is presented in this high entropy oxide material. So that comes to our strategy of designing new high entropy DRX cathodes. When it comes to the composition design of DRX material, we usually need to consider 4 different aspects: lithium excess level, redox active center, D0 charge compensator, as well as fluorination level. And in this study, I use lithium 1.3 as the lithium excess because it will guarantee enough amount of percolating lithium, while on the other hand, do not put too much limitation on the transition metal redox capacity. And we also use fluorine 0.3, that is 15% fluorine substitution in order to increase the amount of transition metal redox. And in the baseline compound, we combine manganese 3+ and titanium. And to further increase the entropy, that is to incorporate more transition metal species, now we have manganese 2+ as well as niobium so that they can reach charge balance. And we can also add another 2+ cobalt and also a 3+ chromium so that the entropy can be further increased. And these 3 materials will be noted as TM2, TM4, and TM6 based on the number of transition metals incorporated inside the structure. All 3 materials can be synthesized through traditional solid-state method. And here is the XRD pattern of the 3 materials, and they all show overall DRX structure without any observable impurity signals. And the particle size of the synthesized materials of all the 3 compounds is around 5 to 10 nanometers, and that can be reduced to around 200 to 500 nanometers after ball mill. And the EDS mapping of the TM6 as a representative shows that all the elements distributed uniformly through the particle. To characterize the short-range order in those three materials, we took electron diffraction of the synthesized material. And as we can see, in those electron diffraction patterns, the round spots represent the long-range ordering, and we can see both TM2, TM4, and TM6 show the same long-range ordering, while this square-like diffuse pattern represent the short-range order feature. And we can see when we move from TM2 to TM4 to TM6, those intensity of the diffuse pattern significantly reduces. In other words, the short-range order in the material can be reduced when we incorporate more transition metal species. A quantitative analysis to integrate the short-range order intensities also clearly show us that the short-range order feature significantly reduced from TM2 all the way to TM6 when we have more transition metal species. As a consequence of the reduced short-range order, we can see the electrochemical performance from TM2 to TM6 can be significantly improved. When we cycle between 1.5 to 4.7 volt at 20 milliamp per gram, TM2 shows the capacity of 220 milliamp per gram and a specific energy of around 700 watt-hours per kilogram. This can be improved to a capacity of around 270 milliamp per gram and a specific energy of around 850 watt-hours per kilogram, and can be further improved to larger than 300 milliamp per gram and a specific energy of larger than 950 watt-hours per kilogram. At the same time, the rate capability can also be significantly improved. For TM2, when cycling between 1.5 to 4.7 volt, the capacity reduces around 60 to 70% when you increase the rate from 20 milliamp per gram to 2 ampere per gram. While this capacity reduction is reduced to slightly more than 50% for TM4 when you increase the rate from 20 milliampere per gram to 2 ampere per gram. And this capacity reduction can be further reduced to around 40% in TM6 when you increase the rate all the way to 2 ampere per gram. And remarkably for TM6, even if when you cycle at 2 ampere per gram, it still shows a discharge capacity around 170 milliamp hours per gram. And this proves that DRX material is not only a slow material, but it can achieve high rate capability if we somehow optimize the short-range order. Now here we want to carefully evaluate the entropy effect and to prove that it is not the incorporation of a specific transition metal species that lead to the improvement of the capacity. In the first group of comparison, we compare 3 binary systems, manganese 3 plus titanium, manganese 3 plus niobium, as well as manganese 2 plus niobium, to the quaternary system, which combines all 4 transition metal species, manganese 2 plus, manganese 3 plus, titanium, and niobium. Here we want to mention another binary system, manganese 2 plus titanium, cannot be successfully synthesized because it always contains another secondary phase impurity, lithium fluoride. And here we can see the TM4 compound, which contains all 4 different transition metals, have a higher capacity and energy density compared to all 3 binary systems, which means it is the entropy effect that help to achieve a higher capacity here in TM4. In the second group of comparison, we compare two different TM4 compounds. The first one contains manganese 2 plus, manganese 3 plus, titanium, and niobium. And the second one contains cobalt 2 plus, manganese 3 plus, titanium, and niobium. We compare those two compounds with another TM5 compounds, which contains all 5 elements that involves manganese 2 plus, cobalt 2 plus, manganese 3 plus, titanium, and niobium. And we can see these TM5 compounds shows a higher capacity compared to both of the TM4 compounds. This proves cobalt itself cannot explain the improved capacity from TM4 to TM6. And similar proof has also been done to demonstrate that chromium itself does not account for the improved capacity from TM4 to TM6. And this is achieved by comparing the TM6 compound with two chromium-contained TM3 compound at the same chromium concentration. And by these 3 groups of comparison, we can strictly prove that it is actually the overall entropy effect rather than the incorporation of a specific transmetal species that leads to the improved electrochemical performance. Now we know that mixing various different transition metal species can be beneficial for the lithium transport in DRX material. However, when you are reaching a higher dimensional chemical space, you have to face this capability issue. That is, whether two transition metals can be compatible within the same structure. And in order to provide some further guidance for future compositional design for high entropy DRX cathodes, we did this compatibility analysis. Here we are focusing on 2 parts of the compatibility issues. The first aspect we need to pay attention to is the redox capability. For example, when manganese 3 plus is in the same structure with vanadium 3 plus, because of their difference in equilibrium potential, charge transfer will happen between manganese 3 plus and vanadium 3 plus, oxidizing vanadium 3 plus to vanadium 5 plus while reducing manganese 3 plus to manganese 2 plus. And this tells us that manganese 3 plus and vanadium 3 plus are not redox compatible, so they should not be put in the same composition when you design the high entropy DRX materials. And all the transition metal pairs that are not compatible in a high entropy DRX lattice has been marked in gray color in this heat map. And the second part of compatibility we need to pay attention to is a chemical compatibility. So when 2 transition metal species come together in a high entropy DRX material, instead of forming the disordered rocksalt structure, they may form some competing phases which are somewhat dynamically more stable. So we say that this transition metal pair is not chemically compatible in high entropy DRX. In this heat map, we represent the chemical compatibility by the color scale. So if the color is more reddish, it means those transition metal pairs are not that compatible in terms of chemical stability. When the color is more greenish, it means those 2 transition metals are compatible based on chemical stability. We have also provided an interactive version of this heat map online, which can be found on this website. And basically, when you put your mouse on a specific square, it will show you like all the possible competing phases based on our calculation results, which is pretty helpful for future composition design. And based on our compatibility analysis, we successfully synthesized a DRX compound that containing 12 different transition metal species, including manganese 2+, cobalt 2+, magnesium, manganese 3+, chromium, iron, gallium, titanium, zirconium, niobium, antimony, and tantalum. The XRD pattern shows that it forms a pure DRX phase with no observable impurity. And also the TM-EDS mapping shows that all the elements distributed uniformly in the lattice. And these experimental results demonstrate that the DRX material actually have very good structural stability against disordering, which allow us to incorporate various different transition metal species to improve the lithium transport. However, we have to note that this composition is not optimized for a better electrochemical performance, but just as a proof of the synthetic acceptability of super high entropy DRX materials. Here we also outline a couple of suggested design principles for high entropy DRX cathodes. First, we would suggest to apply a lithium excess level of around 1.2 or 1.3 formula unit in order to provide enough amount of percolating lithium, but without too much limiting the redox capacity on transition metal. And also, we may consider to use fluorination to further increase the amount of transition metal redox reservoir. Regarding the choices of specific transition metal species, we would suggest to prioritize the use of redox active transition metals so that it can facilitate the lithium transport without sacrificing transition metal redox capacity. To summarize our key findings in this work, first, we designed and synthesized 3 prototype DRX oxyfluoride cathodes with different transition metal species, 2, 4, and 6. We further used TM electron diffraction to confirm that when you have more transition metal species, you will have less short-range order. And the reduction in short-range order as a consequence lead to improved electrochemical performance from TM2 to TM6. And specifically for TM6, it achieves high energy density larger than 950 watt-hours per kilogram, and also excellent rate capability, which demonstrates larger than 170 milliampere hours per gram when cycling at a high rate of 2 ampere per gram. And this very large chemical space naturally leads us to a compatibility analysis. Basically from 2 aspects, the redox compatibility and the chemical compatibility to provide useful guidance for future composition design within this high entropy DRX class of material. And based on the compatibility analysis, we also successfully synthesized a DRX compound containing 12 different transition metal species as a proof of concept. And finally, I would like to acknowledge our funding sources from Umicore as well as US Department of Energy. And I would also thank the experimental resources provider, Lawrence Berkeley National Lab, Advanced Light Source, Argonne National Lab, and the neutron source at Oak Ridge National Lab, as well as a synchrotron source from Brookhaven National Lab. And here I also listed the recent publications from our group on similar topics of DRX cathode materials. So if you have any questions or suggestions to our work, feel free to let us know. I have listed my email address on the slide. So you're welcome to contact me if you want to have any discussion or collaborations. Thank you.